Hi everyone. In this video we're going to talk about stacks. Now a stack is a classic data structure that is fundamental to some of the most important algorithms of computer science. And it is a collection. It holds stuff, it holds other objects for us, but in particular it's a special kind of linear collection. In some sense it's a special kind of list where you can only put elements in at the end and you can only remove elements from the end. So we call that LIFO, last in, first out. The last thing you put into the stack is necessarily the first thing that comes back out. So one way to think about this is a stack of books, where the stack is so big that it really only makes sense to put things on the top. So as you want to add a book, you stack them up, and the stack gets taller and taller. And if you want to take something off, you have to take it off the top, because if you try to pull it out from the middle, the whole thing will just collapse. I was taught to think of a stack as like a stack of plates at the buffet. You know how they're on that little spring that sinks down into the table, so you really only have access to the top plate on the stack. And as you pull plates off, then they get lifted up. So here's a conceptual view of the stack, just like that stack of books or stack of plates. We can only put things on the top. You can't stick one into the bottom. You can't stick one in the middle. And of course, if you're going to take something off, you take it right off the top. Okay, let me show one more take on a stack, similar to what we've seen before, but it'll be relevant a little bit later in the lecture. And so let's look at a stack as a model for some interruptible processes. All right, so imagine I am sitting in my office, like my real office at Grand Valley, at my desk, and I'm, we'll say, grading paper. So I have a student paper here. I'm reading through it and I'm grading it. Then one of you walks into my office in our former world, where you could actually walk into my office, and you're working on some homework and you have a problem. So what do? You set whatever you're working on, that homework paper, on top of what I'm grading, and we sit down and we look at it and we work through it. Right, and as we're doing that, the director comes in and he has a couple of pages he needs me to read through and get my feedback on it. He's doing something important, needs to be done right now. So he comes in and sets this stack, and we put it right on top of your homework, and I say, give me about 2 minutes. So I look through what Dr. Leidig is asking questions about. And as we're doing that, then the dean walks in. He's in town, he's working on a grant, and he needs my signature on something. So he comes in and he puts his paper on top. So we're stacking all of these tasks up, each as one with more importance comes in, or at least one that needs to be done more urgently. So I sign that paper for the dean, take that off the stack, hand it back to him, and he leaves and goes about his other tasks. And then I can finish reading what Dr. Leidig wanted me to read. So I do that and give him the quick answer he needs. So that comes off the stack, and what's left on top now is the homework that we're working on. And so we finish up the questions that you have, and so then you take your paper and then you head out, and that leaves on my desk what's now at the top of that stack was the papers that I was originally grading. And then when I get through all of those papers I'm grading, then I can take that off my desk. My desk is clean. I can go home and have dinner. So another example of last in, first out. That's where the tasks are interruptible, where something more important comes in and it goes on and gets popped off. This is also how method calls work. If you're running method A and you're running some lines of code of method A, and then you call method B, then you call method B. You run some lines of code for method B. One of those says run method C, so you run method C. When C is done, you come back to B, right? And when B is done, you come back to A. So the methods you're running, in some sense, stack up the same way that there was a stack of paper on my desk. And in fact, as we've mentioned before, inside of the computer, inside of the fundamental way that a computer is put together is a data structure called a stack. It's a literal stack like we're using here that's used to keep track of which method you're running and the local variables and so on, and that's what makes recursion work. So we'll come back to some of these ideas later, but keep this analogy in mind. So the main operations, they have special names that make sense given the idea of a stack. So when you want to add something to the stack, you push it on the top of the stack. like if you were to push those plates down when you put something on top of the stack of plates. When you take something off the top of a stack, that's called popping it off the stack. Again, this is why I kind of like that dinner plate example, because when you pull that dinner plate off the top, the stack of plates pops up a little bit, so the next plate is right there at hand. And then some minor things, of course. It's useful to be able to peek at the top element of the stack without taking it off. That's why it's called peek. We're just looking at it. We're not removing it. You might want to ask if the stack is empty, so you don't try to pop an empty stack, which in Java we usually have that raise an exception. And it's also useful to know how many things are on the stack. So that's not to say you can't add other operations if you implement your own stack, but when we're talking about the core of what makes a stack interesting and unique, these are the operations we're talking about. Okay, so let's talk about what we use a stack for, some of these classic algorithms. So before I do that, a little bit of context. When we write out mathematical expressions, we typically do that in what we call infix order. That means the operator's in the middle. We say, for example, 4 plus 5. We put the plus between the 4 and the 5. So the operator is in the middle, hence infix. But of course you know that infix isn't perfect. We spend a lot of hours in our elementary school and middle school careers learning to deal with those. For example, if I say 4 plus 5 times 6, that's potentially ambiguous, and we need things like the order of operations to tell us that we do the multiplication before we do the addition. And sometimes we even need parentheses. So although it looks nice and we're used to doing it that way, infix isn't necessarily the best way to represent mathematical expressions. Another thing you could do is something called postfix, where you put the operator after the two operands. So if we want to subtract 8 from 15, we could say 15 8 minus, put the minus at the end instead of the middle. And so when we do that, then it's not ambiguous, because if we take the expression that we had before, 4 plus 5 times 6, instead of needing special rules or parens to decide which one goes first, we can use the postfix notation. And so this first one here, the star is closest to the 5 and the 6, so that would give us the equivalent of 4 plus 5 times 6, the standard order of operations. In this case, if we put the plus after the 4 plus 5, then that tells us we want to add the 4 plus 5 first and then multiply the 6. I should probably know the history of how we ended up with infix instead of postfix, even though postfix appears to have some advantages here, but I don't know that off the top of my head. All right, let's see another example from the textbook here where we have this, 3 times 4 minus 2 plus 5, so on. Fairly complicated, lots of parens in there, and we don't need any of them if we use the postfix. So here, if we look at this expression, if we look at it the way we're sort of trained to, we first look to the middle. So we see that 2 plus 5 is in the middle, and we can see that the 2 and the 5 will in fact get added together. Inside of the outer parens here, there's a 3 times 4. The order of operations says that has to go next, and we can see with the 3 4 star that would in fact get done next, and then this minus sign here. So by putting the minus sign there, then we're completing the parens. And then the next couple of steps are just multiplication and division left to right. So we'll multiply by 4 and then divide by 2. So the key point here is that postfix expression is completely well defined without the need for the order of operations and parens and other things that we were used to from our own arithmetic. Okay, so if I give you a string with a postfix expression in it, how can we evaluate it? Think of this as perhaps you're implementing your own graphing calculator or something like that. All right, so you have a string with numbers and operators in it, and then so you'll scan that left to right, maybe like by using a scanner. And so when an operand is encountered, an operand being a number, then you push it on the stack. So I'll draw here. Well, there's a better example coming later, but if it helps, if I have like 4, 6 plus, I'll start reading the string left to right. So if I encounter an operand like the 4, I'll push it on the stack. And then the next thing I read is another operand, so I'll push it on the stack. And then when you get to an operator, like a plus, a minus, or so on, then you pop off the top 2 things on the stack, you add them together, and push the result on the stack, which is a 10. And then when you're all done, like we are here, there should be one thing left on the stack, and that's your answer. So let's look at this example here. So again, we'll read this left to right. So you can see the first thing is a 7, which got pushed on the stack. And then a 4, and it got pushed on the stack. And then the -3, and it got pushed on the stack. And then the next thing is the multiplication operator. So when you get an operator, you pop the top 2 things off the stack, the -3 and the 4. So 4 times -3 is -12. That gets pushed on the stack. And then the 1 and the 5 got pushed on the stack. The plus, so we'll add 1 and 5 to get 6. With the divide, we divide -12 and 6. The -12 came first, so we're doing -12 divided by 6, which gives us -2. The very last step is to multiply -2 times 7, which isn't shown here in this diagram. But if we push that result on the stack, we'd get -14. Our input is empty, and we have one element left on the stack, which is the answer, the evaluation of that expression. Now there's some caveats here, of course. We're assuming that our input is a well-formed postfix expression, so if there's extra numbers or extra operators in there, then this would break down. And so the algorithm isn't looking for any errors, but it gives you an idea of one of the key things we might use a stack for. So how would we implement a stack? Well, there are 2 key ways we can implement a stack. We can implement a stack with an array, or we can implement it with a linked list. So now if we start by implementing it with an array, we have to watch out for the fact that the array may become full, or you could use an array list which can grow. We haven't talked about that, but I think you've probably seen that in CS1. Also, just as a quick reminder, an array of objects is really an array of references. So remember that picture, we did this at the very beginning of the semester. Here's the array. So these are the references here in the array, and the actual objects that we're putting in the stack, whether they're strings or students or whatever, actually live somewhere else. So here's what we're going to do. We'll call this class an array stack, so we know it's a stack. It's implemented on an array. Java doesn't follow that. But what we're going to do is we're going to, in addition to the array, have a instance variable that keeps track of what the working end of the stack is. So the bottom of the stack, I think the first book or the first plate, will be at index 0, and where we're doing the work will be at the end of the array, in which we keep track of with a variable called top. So top, as we add stuff, will increase, and as we remove stuff, will decrease. So here we have a stack where we've pushed A, then B, then C, then D. So in this case, our top is listed as 4. It tells us how many elements are in the array. It tells us where the next thing we're going to push on the stack goes. And then if we were to push another element, if we were to push E on the stack, then it would go where the top said, which is 4, and we'll bump the top up to 5. And then if we do a pop, then of course the top tells us that's where the next one goes, which means the top one must be 4. So we'll just bump that top back down to 4, which effectively removes E from the stack. Now we might not physically remove it, but by moving the top down and saying this is now the top of the stack, we'd be ignoring it. Now notice that this works reasonably well. Because both of these operations are constant time operations. To add something to the stack, you just put the new value in the next spot in the array. That's a big O of 1 operation. You bump up your top by 1. That's a big O of 1 operation. Likewise, to remove something from the stack, you're just grabbing an element in the array, which we can do quickly, and then adjusting that top. Now, this is why, of course, the top of our stack is the larger numbers in the array, because we couldn't do that from the 0 end without having to shuffle everything. Now, with a linked list, the concept is similar. Instead of an array, we have a linked list. We'll mark one end as the top, one end as the bottom. The nice thing about a linked list is that we can work from whichever end we want. It doesn't really matter. Well, it kind of does. So if we have a singly linked list with just a head pointer, then we have to work from the side of the head of the array, because that's the only place where we can both add and remove elements in constant time. If the top is the same as our head, then we can insert elements at the beginning here, and we can make the head jump over that element to remove them. But without a tail pointer, we can't really make changes here in constant time. If we also had a tail pointer, then we could add from the head or the tail, and we just have to pick one. Okay, to finish up, I want to take a quick look at how we can use a stack data structure to replace recursion. Remember, recursion is implemented using a stack that's built into the computer. So if we take that stack that's built into the computer, move it into our software, so that's the key to turning a recursive algorithm into a non-recursive algorithm if you want to do that. So what we're looking at here is the recursive solution to solving a maze. We looked at that a few weeks ago. The key observation here is that once you're standing on a valid space in the maze, you're not standing in a wall, for example, then you mark that as a space that you've tried, and then you recursively search down, then right, then up, then left. And so this stack that you implicitly create when you make these recursive calls are like your breadcrumbs. You walk down the maze whatever way you want, and if you run into a dead end, meaning that you end up at a space that's not valid, then you end up returning from the method, which pops one of those breadcrumbs off the stack, and you end up back where you were before. Lets you do a depth first search through the maze. Now let's say we want to write this in a non-recursive manner. I'm not sure why exactly you'd want to do that, because it's harder to figure out what's going on. But if you're in a situation where recursion is not an option, or you just like puzzles, the book does give a partial solution using a non-recursive approach. So the key here is that you have a stack of elements. In this case, it's a stack of XY positions. That's all that's in that position object. So I won't look into it, it's just XY. And so what you do is you start at 0, 0, and you push that on the stack. Every time you push a position object on the stack, that's like dropping a breadcrumb, it's dropping a marker indicating where you've been. And so while you haven't found the end of the maze, then what you do is you pop the top position off the stack. That's sort of the last space that you can look at. Try position method here is what checks for validity and sees if you've been there before and all of that. And so what it will look at is if that space that's at the top of the stack happens to be the exit to the maze, then you're done. Otherwise, it pushes the 4 possible directions you can move onto the stack. That in some sense puts them on your list of possibilities to try. That's all that happens here. The while loop comes around. You're not done yet. There's obviously stuff on the stack. So then it will work through, pull the top one off to see if you happen to stumble across the solution. Now, I'm not a big fan of this particular solution because it doesn't line up exactly with the recursive version. Notice here that we're just blindly pushing all 4 directions onto the stack so they all 4 get tried. Whereas in contrast, the recursive version would try a direction, see if you found a solution before it tried the next one. This isn't a perfect analogy, but I hope it gives you an idea of how you can use a stack to do something similar to a recursive method where the recursion is more than one recursive call per loop. Right. Remember here that as we go through the loop, we can make up to 4 recursive calls, so that builds a tree. That's the more challenging recursion style to undo. The other thing I don't like about this particular solution is that when you're done, you don't have a path through the maze. When it goes and just blindly tries all four directions like it does here, you don't get the solution. You just get a yes or no as to whether it's traversable. I wonder if the authors intended to make the solution part of this an exercise. I didn't see it in the book, but I might have overlooked it. Anyway, although this isn't perfect, I think it does give a decent idea of how you would go about replacing recursion with a stack. If that's a puzzle that you want to dig into a little more deeply, it is an interesting problem. I've had fun working on problems like this before, and I'm happy to work with anybody outside of lecture time to do that. Okay, so that should give you a good introduction to stacks. Didn't necessarily cover every last detail. I think the book does a good job of filling in details that you don't necessarily need to both see and hear. But as always, let me know, send me an email if there's anything you want clarification on or more information on.